Okay, welcome everyone. So today I'm going to just finish off a loose end coming from complex analysis, but also make a connection with what is coming after this, which is the Dirac delta function, and also how to take the Fourier transform of the wave function that we saw that I presented in the last lecture. So before I start, first of all, is there any, can you guys hear me okay?
Ji sir.
Okay. And are there any questions from previous time? Okay, if there are any questions, you can always interrupt me in the middle of the class. So, again, I'm going to tie up a loose end coming from complex analysis and Fourier analysis. And in a previous lecture, we saw that the top hat function is this very simple function, which is, we defined it in a little bit of a peculiar way, where the width of the function was epsilon. So this was epsilon minus epsilon by 2. This is plus epsilon by 2. This is x. And the function psi of x, we define the height to be 1 over square root of epsilon. Now, it is more common to see the height of the function to be defined in 1 over epsilon, but we are not doing that. And the reason is because we want psi of x squared, when we integrate it from minus infinity to plus infinity, over x to be normalized. So of course, if I do this, then the height of psi squared will become 1 over epsilon, and then that would be normalized. So that's the reason why our height of the top hat function is 1 over epsilon square root rather than 1 over epsilon. Okay? So in a previous lecture, we saw that by a very easy and basic algebra, that the Fourier transform of this function is given by the Sinc function. So with all the epsilon, this is how we define our Sinc function. So the Sinc function is essentially a function which has the sine of x, or sine of k in this case in the numerator, divided by k. And for good measure, we throw in a factor of epsilon by 2. But this factor is unimportant for the definition of the Sinc function. So I don't know if it's called Sinc or Sinch. I think Sinc. It may even be pronounced Sinc. So this is how it's how this is spelled. So it's fairly easy. Okay, before I look at the Fourier transform of this function, let's make some comments. And comment number 1 is that the width of the top hat function is epsilon. And to find the width of the Sinc function of the Fourier transform, what we have to do is that we have to find the first zeros of this function around the origin. So what does this function look like? At the origin, this function is not singular because, as we know, when sine is very small, when the argument is very small, sine of x divided by x, when x is going to 0, the first leading term is x by x, so this is 1. So at the origin, this function is not singular, even though it has a 1 over 0 in the denominator. Okay, so this function looks something like this. Okay, so it's good. Okay, and so the width, we can take a reasonable measure of width, and this, I choose this to be delta A, that is the distance between the first zeros of this function above the origin. And that, if you calculate, it's 4 pi by epsilon, okay? So this shows that the product of the top hat function and the product of the sinc function is 4 pi. And what is important is that this is independent of epsilon, right? So if epsilon is a parameter, so if I take epsilon to 0, what happens is that, or take it smaller, the width of this function becomes smaller and smaller, but the height grows in such a way that this norm remains invariant because this norm is independent of epsilon. And similarly, you can show that the square, the norm of this function, is also independent of epsilon, and it also is unity. And that follows from the fact that this is obtained from Fourier transform, and Parseval's formula tells us that the norm of this function is equal to the norm of this function, and therefore, if this function is normalized to be unity, its Fourier transform is also normalized to unity. Okay, so this is comment number 1. So comment number 2 is that the height of, say, psi squared is 1 over epsilon, as I said. Whereas the height of a squared is epsilon by 2 pi. So we see that their heights are also reciprocal. The heights of the norms are also reciprocal of each other. Okay. Now, it was fairly easy to go from psi of x, the top hat function, to a of k, doing a Fourier transform, right? Because this is just a constant function. So all we have to do is just integrate it between minus epsilon by 2 to plus epsilon by 2. And we found this function. But what about the other way? What about going from a of k to psi of x using the Fourier transformation? That turns out to be a harder integral, and it's a good example or good illustration of the kind of techniques that we have been learning in complex analysis. Okay, so let's spend a few minutes doing that integral where we take the Fourier transform of ak to find psi of x. So what is psi of x? The formula. So our next topic is the Fourier transform of the sinc function.